Hi everyone, welcome to the latest 7th installment of Realistic Business Forecasting. You may recall that last week I looked at a regression, a simple version with just two variables, one dependent variable and one independent variable. Today I want to take that further and look at what happens if there's more than one independent variable, so three variables or more. So just as a summary of where we were from last week, let's make the screen a little bit bigger. There we go. So this is where we left off last week. We had this simple regression of yield against rainfall, and 81% of the variation in yield was accounted for by the variation in rainfall. Pretty good result. We had coefficients which were both significant, so that's pretty good. But then the question arises, can we do better? Can we actually close the gap of 19%? So I'm not an agricultural expert by any means, but sunshine, I'm pretty sure, does have an influence on how well crops grow. So I managed to get some sunshine data as well as rainfall for these 10 observations. So what happens if we run the numbers? Well, we can see that we've got a significant increase, and we have closed the gap quite a lot. Before we had 81% of variation in yield being accounted for by our independent variables, and now it's gone up to 88%. So that's a 7 percentage point improvement. We now do use this middle bit, the ANOVA section. We don't need to worry too much about it. Just look at the significance of the F in the last column there. And you can see it's well below 0.05, 5%. So we're happy. We don't need to worry about that. And finally, let's look at the coefficients of the variables. I'm going to leave intercept to one side for a minute. But rainfall and sunshine, you can see that in both cases, the p-value is below 0.05, just about in the case of sunshine, but still it's below 0.05. So we're happy that both of those coefficients are significantly different from zero. Now, how about intercept? If you look at the intercept value, you can see that the p-value is through the roof. So that is telling us that we have an intercept which is not significantly different from zero. But then if you actually think what we're trying to achieve here, we're trying to achieve a model of how yield varies with rainfall and sunshine. And if rainfall is zero and sunshine is zero, then we would expect pretty much zero yield anyway. So in this case, I'm quite happy with an intercept being zero. So this is a good result overall. Now, you may have noticed that there were two lines. There was in the results as R square and adjusted R square. And let me just briefly explain the difference here. Now, with the standard R squared, you can add pretty much the worst variable on the planet, and it will show some small increase in the R square. And that's not a particularly good outcome, because what we're after is a quality regression. Now, what I've done here, I've introduced a new rainfall variable, which I've called rainfall plus 1 day-ish. And you can see that those two independent variables, rainfall and rainfall plus 1, are incredibly highly correlated. In other words, the second rainfall variable adds nothing really to this regression. So let's compare the two outputs, rainfall against yield and the two rainfalls against yield. Now, if you look at the R square, you can see that there is just about a very, very slight increase in R squared, as I said would happen. But the adjusted R squared, which does take account of the quality of the independent variables has shown a reduction of about 2.5 percentage points. So what I always do, I always consistently use adjusted R-square, and that enables me to compare one regression trial with another consistently. So I recommend you do the same. Now, if we think again about some of the tests we need to do, let's start with the sign test. Rainfall still has a positive coefficient, which is what we'd expect. In other words, the more rain we have, apart from floods, obviously, we'd expect the coefficient to be positive. And again, sunshine. Generally, sunshine is good, so more sunshine, better crops, better yield, and the new sunshine variable is also positive. So say these do make sense. Now, I have myself been in situations where I've got these great results, everything's good, high R squared, significant coefficients, and then actually look at the coefficients and then, hold on, is this the right sign? And let me give you a very good example. If you look at the relationship between speed and traffic volume, clearly as traffic volume increases, speed will decline. But if you get a positive coefficient for traffic volume, then something is seriously wrong and you've got to really check out the model or the data and get new data or find a new model. So the sign test is very simple, but can be very important, and it will stop silly mistakes being made. Now, I apologize for what's coming up next, multicollinearity. That's its full name. And the question is, how interdependent are our independent variables? Now, with the example I showed before, with rainfall and rainfall plus 1, you could see that they were incredibly highly correlated, 0.995, and so the second rainfall variable was pretty useless. Now, when you're looking at the correlation between independent variables, you are going to get some correlation. It can't be avoided. And if you actually just run the numbers between the standard rainfall variable and the sunshine variable, you get a correlation of minus 0.54. First of all, the sign looks right, but more importantly, the value is fairly low. With just 10 observations, a value of minus 0.54 is not that high. If you want another extreme example, imagine someone decides to assess property prices as a function of floor area and the number of rooms in the property. Now, again, you'd expect a link. So a studio apartment would obviously have, say, I don't know, 30, 40 square meters, whereas a hacienda with 10 bedrooms and 5 bathrooms and goodness knows what is going to have several hundred square meters. So those, we would expect floor area and number of rooms to be very highly correlated. So you would not include both of those variables in your analysis. Now, there are various tests for multicollinearity and they are quite subjective. So all I would advise here is just using a little bit of judgment, really, as well as undertaking a correlation table. And it's quite easy to develop a correlation table in Excel. Data analysis correlations will actually generate a set of correlations between all variables. So it is quite a straightforward thing to do. Now, let's look at the residual values of the 2 variable and the 3 variable cases. And I've drawn them both on the same chart here. Now, they're both showing a sort of random pattern, which is good. But the blue line, which is a 3 variable residual pattern, does look a little bit better than the black dash line with just 2 variables. So how can we actually check this? Now, again, there are so many ways to do this. So I'm just going to focus on one way of doing it, which is the mean absolute deviation. So we have the residual. So it's the model minus the actual. We take the absolute value and we make sure that the value in the last column is positive, the absolute value. We sum up all the values and take the average. So the mean absolute deviation is 0.55, and this is for the 3-variable case. If you do the same analysis on the 2-variable case, the MAD comes out at 0.92, which is somewhat higher. So not only has the 3-variable case improved the way that our independent variables influence yield, the residuals are higher quality as well because the MAD is lower. Well, that's quite a lot for you to take in. I do apologize for that, but I wanted to get that out of the way, and it was a sort of neat continuation of the previous podcast. So thank you all very much for watching, and the next episode will be on its way soon. Bye for now.